Good afternoon, everyone. I am Devashish Gupta, and today I will be presenting our work titled Scalable Knowledge Graph Construction from Unstructured Text, a case study on artisanal and small-scale gold mining. In this presentation, I will walk you through the motivation behind our work, the methodology we developed using large language models, and how we applied it to a real-world domain to create and validate a domain-specific uh, specific knowledge graph. Let me start with the problem. By 2025, it is projected that over 80% of all enterprise data will be unstructured. Think of reports, articles, emails, and transcripts. Despite this abundance, most of this unstructured data remains underutilized, and largely because it lacks structure, making it hard for machines or analysts to extract value from it. One major challenge is that annotating this huge unstructured data to convert it into something usable like structured knowledge is both labor intensive and requires domain expertise. This makes the process non-scalable for many real-world applications. And this is where recent advances in large language models come in. LLMs such as GPT-4, Llama are now capable of understanding complex text and extracting semantic relationships, entities, and actionable insights even from highly domain-specific content. To organize this extracted knowledge meaningfully, we rely on knowledge graphs, which structure the data into interpretable triplets, which is subject, predicate, and object. These graphs support visualization, semantic querying, and deeper reasoning. However, constructing these graphs and verifying their correctness typically requires human experts, making it difficult to scale across domains. And yes, that leads us to our key motivation. We aim to build a domain agnostic pipeline that leverages LLMs to extract structured knowledge from raw text and introduce an unsupervised validation method called DAS or data assessment semantics, which verifies the factual accuracy of the extracted information using web-scale sources and majority voting, thereby minimizing or eliminating the need for expert involvement. So before diving into our method, let me briefly explain what a knowledge graph is. A knowledge graph or KG is a structured way of representing knowledge where entities like people, concepts, or objects are nodes and relationship between them are edges. For example, like in the sentence Albert Einstein developed the theory of relativity, we can extract a triplet like Albert Einstein developed theory of relativity. This way, we go from messy, unstructured sentences to a structured network that machine can reason over. And knowledge graph helps us to store, organize, and query data efficiently, especially when dealing with large textual corpora. So our first contribution is an unsupervised knowledge graph extraction pipeline using LLMs. So we design an ontology guided prompt to help the LLM model to know how to extract structured triplets, subject, predicate, object from raw text. This avoids any need for pre-level training data. Each sentences is passed through the LLM, which with this consistent prompt, and we collect the resulting RDF triples. To reduce the redundancy and improve the quality, we filter out duplicates and semantically equivalent sentence that make sense. And this makes the pipeline scalable, generalizable, and domain independent. And this is an example of knowledge graph extraction and that looks like on ASGM, our case study that I will describe more in later slides. Okay, so we have extracted the knowledge, structured knowledge from unstructured document, but what is next? So it's obviously validating it. So we propose DAS, data assessment semantics, and unsupervised domain agnostic validation framework. So now let's get into how it works. So first, each triple, which is subject, predicate, and object, we generate a search query. And we retrieve the relevant documents from the web using the search engine. Then we use the PageRank to score and filter the top credible sources. These documents are summarized by LLM. We ask this to evaluate the triple's validity in that context. And finally, we use majority voting across the sources to decide if the triple is factually correct or not. And this allows us to validate information without needing domain experts, making it scalable for any field. So we benchmark our DAS validation approach using Codex S dataset, which contains challenging factual triples. Compared to five existing KG validation methods like TransE, Trackery, Conv, our DAS method outperformed their performance, achieving 91% accuracy. An interesting observation was that DAS also uncovered errors in the label dataset, showing its strength and not just in validation, but also in detecting data inconsistencies. For example, when we are applying our DAS framework on Codex dataset, we saw that for 1,828 ground truth as positive, our model was successfully predicted 1,380 as positive. But it not only predicted that, but also given that this ground truth of 1,828 also contains some labels that are misleading, like wrongly labeled, and that was like around 269 for positive and 47 for negative. So that is a huge improvement, because it also helps scientists to not only validate the factual correctness, also shows any data inconsistency in a data set. So now, to test our full pipeline in real-world setting, like extracting knowledge graph to validating it, we work on a case study in the domain of artisanal and small-scale gold mining, ASGM, which is a critical environmental topic. We collected 9 publicly available reports, and it consists of 930 pages, and we processed them using our pipeline. From this, we extracted 2,653 RDA triples to create our very own ASGM KG, which is based on our knowledge is the first in this domain of mining, gold mining area. Now, to validate the ASGM KG, we randomly sampled 579 triples and asked our domain experts to assess their factual correctness and give the confidence in their validation. These tables help us to evaluate our model in both quantitative and qualitative analysis for justifying robustness. For example, as you can see, we have a triple called Amazon region is ecological treasure. So we asked our domain expert to label it. So they labeled it as a yes. And then we asked like how much confident you were while you were labeling it. And they said like, oh, we are very confident. So we have this confidence score in 4 category. Later I will explain that. So in this table, you can see the 4 category, which is like very confident, maybe, and not sure. So we categorize our all 579 triplets in this 4 category, and then we do some Abelian study. And this table shows that evaluation study we did where we tried with different settings like page rank, majority voting, random selection, and we tested three well-known LLM models like Copilot Pro, Llama, and Mistral. As shown in the table, our method performed consistently well across confidence levels and model variance, especially when combining PageRank and majority voting. This shows the robustness and flexibility of our validation pipeline. One of the remarks is our dash validation framework matched the expert judgment with over 90% accuracy, even when experts express their lower confidence. This not only helps and shows you how this model is work and how fine it is, also it shows the robustness of its validation. To summarize, we propose a scalable under an unsupervised pipeline for converting unstructured text into structured knowledge graph using large language models. We introduce a novel validation framework DAS that uses web-scale evidence and majority voting to validate the knowledge automatically. Our approach performed competitively on benchmark dataset and demonstrate real-world utility in ASGM domain. By removing the dependency on expert validation, we also open the door to faster domain-agnostic knowledge curation, especially in under-resourced or emerging fields like mining. And thank you for hearing my presentation and appreciating my work. I really thankful to the committee to accept my paper and encourage me to do work more in this domain. And I'll say please reach out to me if you have any question. My email address is the first one, and you can also reach out to our corresponding author, my supervisor, Dr. Paul Pauka, in this email, and you can scan the QR code which will redirect to your GitHub code, and also there are details we mentioned there. Thank you so much. Have a good day.